All right, and welcome to the last problem for this playlist. So let's take a look at this, what they're asking us here for. So they're asking us to find the current through I of S from the source, through the resistance, through the capacitor, and then also they want us to find the voltage V here, okay, where they define plus and minus. Right. So there's a lot to unpack here, so let's just go and get started. First things first, let's go ahead and take a look at the source that we had over here. You see this is cosine, so we're good. We go and pull our I of S, kind of just a bit of quick practice from the previous problem. I'm just going to pull this out here. Okay. Just pulling the magnitude value out there, and then we hit a 0 phase angle, so we're fine. So that is our phasor representation for our source current. Okay, so part one is done. Look at that. Boom, pretty nice. Okay. All right. Check that off. Cool. Let's go on to part two. Find I of R. Okay. So, to relate these two, we're going to have to use the impedance value. So let's go and write those out. So Z of R, so it's just going to be R at angle 0. So therefore, it'll just be 100 at angles 0, which is just the same thing as saying 100. That's ohms. Then we have this capacitance value here. It's going to be negative J over omega C. And our omega here is 10 to the 4th radians a second. So let's just go and plug those values in. So 10 to the 4th. And then we had 0.5 times 10 to the negative 6. That's what micro is. Okay. When we do that, we'll get negative J200, which is the same thing as saying 200 at angle negative 90. And that'll be ohms as well. And just as a quick reminder, J squared is negative 1. 1 over J is equal to negative J. Okay. J is equal to 90 degrees. And then negative J is equal to negative 90 degrees. All right. Just fun, useful, awesome relationships at the top up there. Okay, so moving on. If we need to find this current and this current, and we know this current comes in here and breaks up into these two currents, to me that's screaming do a current division. But that could get a little complicated. How about instead if we did our KCL law? So here, there. That'll be I of S. This will be I of R. This will be I of C. Okay? And when we do that, what we're going to end up doing is we will do I S is going to be equal to I of C plus I of R. Okay? And we know from our Ohm's law equation, we can rearrange these to be V over ZR plus V over ZC, right? Because everything is in parallel, they're all going to have the same voltage, all right? So if we go and write these relationships out, it'll be V over Z of R, we said was 100 plus V over negative j 200. All right, and this is important. This is where that 1 over j is equal to negative j comes into play. This will save us a little bit of time from having to convert to phasor and then do a division, and yeah. So if we do this, what we'll have is now 0.01 volts for the first part, and then if we take the negative j bit from right there, we'll replace it with j. We're just using that relation. And then it would be V over 200, so 0.005, and then volts. Right, this is still I of S. And if we were to take these, and let's go ahead and relate these to the phasor. So since this is equal to the I of S, so this is that 0.1 at angle 0. Take this bit, let's turn it into phasor. Okay, and I'll let you get a little bit of practice with it. I'll write it on the side over here as well, so you can practice just converting those over. 0.01 squared plus 0.005 squared, square root of that, 0.01118, then tangent inverse theta is equal to tangent inverse 0.005, 0.01, that'll give us 26.56 degrees. Okay, so now we'll have 0.1 at angle 0 is equal to 0.01118 at angle 26.56 degrees times voltage. Okay, so therefore, let's rearrange and solve for the voltage. Okay, this does seem like a very long, complex way of doing it, but you'll see why we are doing it in just a second. Because what we're essentially going to do is use the voltage to find the current. Okay. So if we do that, we'll have 0.1 at angle 0 divided by 0.01118 at angle 26.56 degrees. So we'll divide the magnitudes. We'll subtract the angles. So therefore, the voltage is going to be 8.94 at an angle of negative 26.56 degrees. And that'll be your V. Okay, so they asked for the voltage, and they got it a little out of order, but that's fine because now what we're going to use is our relationship V is equal to IZ, where if we know the voltage now across every branch, we know the impedance across each one of those, we can just rearrange and solve for the I. So I of R will be voltage over Z of R, which will just be 8.94, angle negative 26.56 degrees, over Z of R, we said was 100 at angle 0, so 8.94 over 100. Negative 26.56 minus 0. That'll give us 0.0894 at an angle of negative 26.56 degrees. That'll be current through the resistance. And we'll do the same thing for the that is a capacitor, for the capacitance. So V over ZC, 8.94, at an angle 26.56 over, we said it was 200, angle negative 90. Okay, we'll get 0.0447 at an angle 63.44 degrees. Okay, that'll be our current through the capacitance. And real quick, let's use that check like we had said earlier. So this is a capacitance. So if we write ICE, so the current leads voltage. And if we take a look, our current is at an angle. So current is at an angle 63.44 degrees. And that voltage is down here at an angle of negative 26.56 degrees. And if we added those two together, we would get our right angle of 90 degrees. And we notice that our current is ahead of our voltage. So therefore, we are good, we are happy, and our answer is looking correct. All right. Well, that concludes this SI session. If you have any questions, feel free to email me, leave some comments. I'll do my best to get to those. Until then, see you later.